Attention pour le décompte final. 3, 2, 1, allumage Vulcain.
Reaching for the sky. Space technology is a great fascination for people all over the world. Today, rockets transport satellites to their locations in space in a matter of hours. Engines generate millions of horsepower to break free of the Earth's gravity. Hundreds of thousands of people work in space programs around the world. Europe also has its own aerospace workhorse, the Ariane 5, Europe's most reliable rocket.
De la télémesure de la station Santa Maria, aux Açores.
Ariane 5 is being transported to her launching pad at the giant spaceport in French Guiana. On board this time are 4 satellites for the European navigation system Galileo. This mission is a premiere for the ESA and the Ariane program. The European Space Agency, ESA, is based in Paris and is responsible for securing Europe's access to space. It was founded by 10 states in 1975 as a counterbalance to the American and Russian space programs. Today, there are 22 nations involved. Access to space has become increasingly important for telecommunications, but also for climate and fundamental research. Participation in the International Space Station program, ISS, in particular, shows that the Europeans are an important partner in space research and exploration. The first European steps en route to space are taken by France with the launch of their Diamant rocket in 1965.
5, 4, 3, 2, 1.
Inspired by its initial success, France quickly spurns the idea of one-nation space travel and gains partners for the next project, the Europa rocket. This has the size and format to challenge the systems operated by the Soviets and Americans. Germany and the United Kingdom are also involved in its development. And so the foundation is laid for a common European launch system. Unfortunately, all versions of the Europa rocket struggle with serious technical problems, and no satellites are successfully put into orbit. But the hard lessons of this intensive learning process are what ultimately lead to the start of the Ariane program. Ariane, derived from the name of the Greek goddess Ariadne, was blessed with much better fortune than the Europa rocket. The first launch took place at Christmas 1979. This is also the premiere for the Kourou spaceport in the French overseas territory of Guyana. From now on, ESA has its fixed abode here and plenty of space for expansion in the years to come. Ariane 1 is followed by 3 other versions up to the Ariane 4. These rockets increase in power and efficiency and gradually become bestsellers. For their customers, they transport hundreds of commercial, scientific, and military satellites and probes into space until well into the 1990s. Altogether, this series flies 144 missions, a reliability quotient of 96%. Ariane 5 is intended to be Europe's entry into manned spaceflights. For this purpose, the small Hermes space glider is designed at the end of the 80s, but never built. From the mid-1990s, Ariane is ready for operation and replaces its predecessors. Meanwhile, it is the world's most reliable launcher. Its failure rate is extremely low, and that's what makes it so successful. There are currently two variants of the Ariane 5. The ECA version is the one that's used most, with a height of 59 meters, a diameter of 5.4 meters, and a liftoff mass of 770 tons. It is the European Space Program's workhorse. It can bring 2 satellites with a total mass of up to 10 tons to an altitude of 36,000 kilometers. The smaller ES variant is 53 meters in height. It can transport a payload of up to 20 tons to an altitude of 300 kilometers, and will be able to carry the 4 lighter Galileo satellites up to an altitude of 23,000 kilometers. Ariane 5 consists of 2 stages, the main stage and the upper stage. The main stage, EPC, short for Étage Principal Cryogénique, is a giant fuel tank that supplies the Vulcain 2 engine. On the sides of the main stage, there are 2 solid propellant boosters providing the required liftoff thrust. This combination is the same for all Ariane 5 launchers. On top of the main stage is the upper stage. There are currently 2 different versions in the Ariane program, the short EPS variant and the longer ESCA version. The most important component of both upper stages is the control unit, VEB, short for Vehicle Equipment Bay. This is the rocket's electronic brain. Under the payload fairing, the difference between the 2 versions becomes clear. The EPS stage has a compact reignitable Estes engine. On the payload adapter above it, numerous smaller satellites or the large ATV space transporter can be mounted. The ESCA upper stage usually transports 2 satellites at once using an HM-7B engine. The first satellite sits on the large tanks and the payload adapter. A transportation structure, the Silda, covers this, and at the same time serves to accommodate the second large satellite. The payload fairing is variable in length and can be adapted to each specific mission. Ariane 5's liftoff mass of 770 tons is the equivalent of 2 fully fueled and loaded jumbo jets. The boosters, each with their 241 tons of fuel, enable Ariane to lift off very quickly. Their thrust, enough to lift a mass of more than 1,200 tons, is the equivalent of approximately 45 million horsepower. Within 140 seconds, the launcher reaches a height of 65 kilometers, and many times the speed of sound. The booster is a 30-meter-long pipe with a 3-meter diameter. It's filled with ammonium perchlorate and aluminum powder, with a rubber-like artificial resin as the binder. Ignition takes place in the top of the booster, and in 0.36 seconds, flames shoot out through the entire booster interior. Burning from the center outward results in temperatures of 3,000 degrees and pressure of up to 65 bar. An Ariane launch generates huge quantities of exhaust gases and heat, as well as shock waves. The launch pad must be able to absorb these enormous forces in the initial few seconds of a rocket's flight. The ELA-3 launch complex in French Guiana has been in operation since 1995. Reinhard Hildebrandt has been here from the very beginning and has worked on the Ariane program for more than 30 years. In Kourou, he is responsible for the Ariane 5 rocket's final assembly and accompanies it right up to the launch pad.
We are standing here in the exhaust duct. It's possible now, but certainly not during the launch. The reason it's so big is that each booster burns 2 tons of fuel per second, so the exhaust gas and smoke emissions must be channeled out of here. It has a funnel-shaped design, and the dimensions for constructing the duct needed to be calculated precisely. Lots of concrete, lots of iron, and yet there's still a lot of maintenance afterwards, as everything has to be renewed.
From this concrete colossus, an Ariane rocket is launched into space between 6 to 8 times a year. Shortly after launch, the Ariane 5 turns and banks into its predetermined flight path. All in-flight processes are pre-planned and controlled by the onboard computer, making Ariane 5 completely autonomous. The boosters are given the command to jettison after about 2 minutes at a height of around 65 kilometers. These burned-out auxiliary engines then splash down into the Atlantic a few hundred kilometers from land. The main stage now provides the propulsion for the remainder of the flight. Thousands of data packages travel back and forth between engines, sensors, and onboard computers and are synchronized with the flight program. This cylindrical segment is assembled in Bremen, Germany. Its official name is Vehicle Equipment Bay, VEB. Despite its size and its weight of 1.5 tons, it is relatively light and intricate. On the inner side, a gold-colored insulation membrane protects the computers behind it from too much thermal radiation. The 5.40-meter diameter of the rocket provides sufficient space for the computers and electronic control systems. All devices installed here are double redundant, which means that even if 2 devices fail, there is still a third available in reserve. The processing power of the onboard computers is not even as high as that of a smartphone. The processes don't need it to be. The computer deals with great quantities of data from countless sensors, but doesn't need to operate graphics for monitors and displays, for instance, and so can concentrate fully on control operations. And these onboard computers are extremely robust. Behind their thin layer of insulation, they can withstand the vacuum that is outer space and temperatures as low as minus 270 degrees. The heat of the engines and the sun doesn't affect them either. The brain of the launcher steers the central stage of Ariane 5, which provides the flight's longest acceleration phase, reaching up to 24,000 kilometers per hour. The main stage, also known as EPC, is manufactured in France. The town of Les Mureaux lies on the Seine, 40 kilometers from Paris. In 3 giant bays, the Ariane 5 main stages are assembled. This large plant also produces many other components for the 6 to 8 launchers each year. In this extra high hall, the gigantic high-tech main stage is put together, completely by hand. It takes around 9 months for a main stage to be completed. The largest component is the enormous aluminum tank. It is extremely light and yet can hold 600,000 liters of super cold fuel, which is also highly pressurized.
In aerospace, lightweight construction and selection of materials are extremely important. Get this right, and then it's possible to transport hundreds of tons of rocket fuel, even if the tank itself only weighs 6 tons.
The main tank is divided into 2 segments. The large segment in the lower section holds 25 tons of liquid hydrogen. Separated by a chamber wall, the liquid oxygen is situated above it. It has a mass of 145 tons, but because oxygen is 16 times heavier than hydrogen, it requires a much smaller tank volume. The starting material for the tank is rolled sheets of high-grade aluminum alloy, 2 to 3 centimeters in thickness. The 18 square meter components are vacuum lifted onto a flatbed milling machine by crane. 21 sheets are needed to construct the cylindrical outer shell of an Ariane fuel tank. The milling procedure takes 10 hours per sheet because each one needs its own special profile. The finished aluminum sheets are now 2 millimeters thick, but their edges are considerably thicker. There are also some protrusions left in the material where partition walls and sensor brackets will be welded on later.
The tolerances are extremely low, as we have to work precisely to within 1/100th of a millimeter.
After the sheets have been milled and cleaned, they are formed into cylindrical segments. This takes place on a special forming machine, which shapes each tank segment centimeter for centimeter into a perfect third of a circle. This high-precision processing avoids cracks and material fatigue. 3 sections are then welded to form a ring. 7 of these rings make up the 30-meter cylindrical tank. This takes 5 weeks, a long time, but this cautious approach prevents thermal warping in the individual elements. The partition wall between the oxygen and hydrogen tank is now in place, and the entire tank is sealed with the semi-conical bottom segment. A special crane with 48 suction pads now grips the component gently and precisely. The very thin material makes the tank extremely delicate. A soft drink can of the same size would be 10 times more stable than an Ariane 5 tank. The tank will later contain liquid gases, hydrogen at minus 253 degrees and oxygen at minus 183 degrees. The slightest rise in temperature will return them to their gaseous state. To prevent this, the tank must be insulated. This is done with 250 sheets of expanded polyurethane that cover the tank completely. These are the special ultralight polyurethane sheets which are bonded to the outside of the finished aluminum tank.
It's carried out by 15 employees who take half a day to cover the entire tank and the tank floor with all these sheets.
Finally, the insulation is given an anti-static coating. This special paint prevents the Ariane 5 from becoming charged with static electricity caused by atmospheric friction during the launch. 24 hours before each launch, the fueling process for the main stage begins. Liquid hydrogen and oxygen flow continuously into the tank right up to the final second. The umbilical arms and fueling lines remain attached right up until liftoff. This will ensure that all the launcher's tanks are filled with the maximum volume of fuel. The main stage tank supplies the Vulcain 2 engine. Hydrogen and oxygen are fed to the engines by 2 turbopumps. From there, 566 injector nozzles shoot the mixture into the combustion chamber where it is ignited. The engine has been optimized for deployment outside the Earth's dense atmosphere. It generates 150 tons of thrust, comparable to 4 million horsepower for 9 minutes. In this time, the rocket accelerates to 7 times the speed of a rifle bullet, 24,000 kilometers per hour. Bavaria, the south of Germany, is renowned for its high-technology centers. In Ottobrunn, near Munich, the combustion chambers are manufactured for the 2 most important Ariane 5 engines. The Vulcain 2 for the main stage and the HM7B for the upper stage. Both are cryogenic. That means they operate on supercold hydrogen and oxygen. The Vulcain 2 engine starts life as a rolled and ground metal pot made of a copper-silver zirconium alloy. Its vase-like shape does have some resemblance to a combustion chamber. Before going through the complex production process, it merely undergoes pre-machining, giving it a smooth surface to allow precise material testing. The ultrasonic test shows there are no material defects that would render the combustion chambers useless. For this, the copper blank is lowered into a water tank. Using a highly sensitive ultrasonic transducer, the testing engineers closely examine the rotating blank's material walls. The two engineers are on the lookout for cavities and inclusions. And in one position, the amplitude does actually show a defect inside the workpiece. The position of the defect is then marked for further processing. It is 4 millimeters in size. Only 0.8 millimeters would still be permissible. The defect's coordinates are recorded in the digital planning process. The impurity or cavity will be removed in the coming processing stages by means of turning or milling. To prevent the combustion chamber from melting during engine operation, it must be cooled. For this, a total of 468 cooling channels in 3 different widths are milled into the copper body. Producing them takes the engineers about 12 hours. Inconspicuous as they may seem, these channels are the combustion chamber's most important structure. The liquid hydrogen that flows through them is what cools down the enormous temperatures the chamber reaches. After milling, the channels are completely filled with a special black wax. A thin copper coating and a slightly thicker nickel coating are applied over this later. The excess wax is scraped off so that only the milled channels remain closed. The wax prevents copper and nickel from penetrating the cooling channels during the coating process in the galvanizing plant. In the electroplating tanks, electrochemical processes take place. The combustion chamber is now being coated, a similar process to galvanizing or chroming. This Vulcain 2 combustion chamber is currently immersed in a copper sulfate solution. It is given a copper coating of 1/10 of a millimeter, which lays itself on top of the wax-filled cooling channels. The combustion chamber now passes through the various electroplating tanks. Most are filled with nickel pellets in an electrolyte solution. The pellets dissolve over the course of a few days, and the nickel ions this releases spread through the solutions and form a deposit on the surface of the combustion chamber. These nickel chips go into the electroplating tanks. There, they dissolve, and the nickel is deposited on the surface of the combustion chamber. Each coating requires approximately 250 kilograms of nickel. So for several layers, that can mean almost a ton. The combustion chamber is now completely covered by the dull gray layer of nickel coating. The nickel's high density makes it extremely robust, perfect for use in rocket engines. The thickness of the nickel coating amounts to several centimeters. The wax is then melted out, and part of the nickel is later machined off. At the thickest points, pipes and flanges are welded on. The clean room, Here, the injection head is fitted onto the nickel-coated combustion chamber. It has 566 injection nozzles, which later dispense the hydrogen-oxygen mixture into the combustion chamber. The injection head is attached to the combustion chamber with 60 silver-plated bolts. The silver serves as a lubricant. This completes the pre-assembly of the Vulcain II in Ottobrunn, Germany, and the combustion chamber is then delivered to France. Vernon, in Normandy. In the middle of a remote woodland area lies France's most important plant for rocket propulsion systems. This is also the home of the largest testing facility for cryogenic engines. Besides manufacturing engines for military rockets, the plant also specializes in the production and assembly of engines for the Ariane 5. The combustion chamber from Germany is the heart of the Vulcain II engine. It sits here, surrounded by an entire network of pipes, cables, and sensors. The engine testing facility is located at a safe distance from the manufacturing plant. In this tower, they are meticulously tested down to the tiniest detail before they can be bolted under a rocket. The high-security site is situated deep in the forest, well away from towns and villages. The test tower is also the final production line for the engine. Settings and adjustments performed here will then be found on whichever Ariane 5 is fitted with this very engine. The most important criteria is the functioning of the turbopumps. They pump the hydrogen and oxygen from the tanks into the engine's combustion chambers. At almost 4 meters in height, the Vulcain II engine takes up several floors of the testing tower. Every engine intended for space travel must be tested here first. Test firing is sometimes repeated several times and can last for up to 10 minutes. It is the final check of the correct functioning of the combustion chambers, the temperature distribution, and the operation of the injection nozzles and turbopumps. Every second, 300 kilograms of fuel are forced into the combustion chamber. In the process, the tower discharges 1/4 ton per second of water vapor, which is generated by the combustion in the engine. The energy that quite literally evaporates here later provides the thrust with which the engine and the main stage increase acceleration in the vacuum of space. While the main stage continues to accelerate, the so-called fairing, the payload's protective casing, is jettisoned. A few minutes later, the main stage also separates. This then starts to rotate, and after orbiting the Earth a few times, it splashes down in the Pacific. Now only the rocket's upper stage is flying. To surge deeper into space, the HM-7B engine is now fired into action. Back in Ottobrunn, Germany, besides the combustion chamber for the Vulcain II, the smaller version of the HM-7B engine is also manufactured here. The small nickel-plated combustion chamber is about to undergo a stress test. This involves it being taken from an oven at 90 degrees Celsius and immersed in an ice-cold tank of liquid nitrogen at minus 196 degrees. If the chamber remains undamaged, it can progress to the next processing stages. The HM-7 is a space travel veteran and was previously deployed in the upper stage of Ariane 4. Strictly speaking, the large Vulcain II engine is a further development of the smaller HM-7. The most conspicuous component of the upper stage engine is the expansion nozzle. Its conical shape immediately makes it look like a rocket engine. The nozzle is located behind the combustion chamber. The highly pressurized ultra-hot gas streams out and accelerates to several times the speed of sound. The nozzle bundles this kinetic energy, creating the propulsion for the upper stage in the vacuum of outer space. The nozzle consists of 242 fine pipes of 4 millimeters by 4 millimeters with a wall thickness of 0.3 millimeters. During the flight, some of the liquid hydrogen flows through these pipes, which also has a cooling effect at the same time. This man makes these pipes, some even by hand. First, he bends each of them into a special shape. The curved pipes are then combined on a cone to form bundles. The bundles are surrounded by a tightly wound support wire. This compresses the pipes into the precise cone shape required. During welding, the support wire is removed again. 15,000 weld seams, each 5 centimeters long, hold the super light, delicate structure of the HM7B expansion nozzle together. In the end, that results in a total seam length of 750 meters. Before going into series production, every engine is tested and certified. That takes place in Lampoltshausen near Stuttgart in Germany. Here, engineers are testing the latest rocket engines. They are to be used in future to drive the upper stages of a new Ariane generation. After only fractions of a second, the plume of exhaust gas forms a distinctive cone, the so-called Mach diamond. This indicates that in normal atmosphere, the gases are surging out at several times the speed of sound. Installation of the upper stage engines takes place in Bremen, Germany. This is where not only the brain of the rocket is installed, but where the entire upper stage is put together and prepared for transportation to French Guiana. Before setting to work on the upper stage, the technicians put on special working clothes. They then step onto an anti-static device, which sends a low electric charge through them to make sure their special shoes do the job. This is to avoid any buildup of static electricity and to prevent sparks. The production hall in Bremen is one enormous clean room. It is slightly pressurized to prevent dust and moisture from penetrating the room. Today, an HM7B engine is being installed in the upper stage. For this purpose, it is carefully secured in a transport frame. Costing around 1 million euros, this engine is the heart of the most used upper stage in the Ariane program. A high-pressure hose is unrolled and attached to the transport cage. So as not to contaminate the clean room, only abrasion-free tools and equipment may be used. Compressed air at 6 bar flows into the hoover pads on the transport frame, raising it by a few millimeters. But that's enough to move the heavy frame by hand and position it underneath the upper stage. Then the ring spacer and the VEB are lowered onto the engine. Later, this upper stage will carry the various payloads into orbit around the Earth or into the vast expanse of space. Ariane 5 is certainly the best-known European launcher system. It has already transported numerous commercial satellites into space and is regularly used as the workhorse for space research and exploration. The best-known project is the Rosetta mission to the Comet Churyumov-Gerasimenko.
In orbit around the comet. The orbiter will continue.
The mission began in 2004. To reach the comet some 500 million kilometers from the Earth, the Rosetta probe needed 10 years. On the way, it also undertook flybys of Mars and 2 asteroids for research purposes. The task of the Rosetta probe was to measure and photograph the comet and to put the lander module Philae onto the comet's surface. After the lander's shaky touchdown on the comet's surface, Rosetta then provided vast amounts of scientific data and breathtaking images. The mission ended in September 2016. Also spectacular were the Automated Transfer Vehicle missions, ATVs, for the International Space Station. In return for use of the ISS, the ESA provided 5 transport vehicles that delivered water, food supplies, fuel, and materials for experiments into orbit 400 kilometers above the Earth. The ATVs weighed over 20 tons, the heaviest payloads ever carried by an Ariane rocket.
3, 2, 1, allumage Vulcain.
Besides supplying the ISS, the space transporters were used to raise its orbit. The space station flies at such a low orbit that friction with the Earth's thin atmosphere constantly drags it downward, a phenomenon known as atmospheric drag. Bremen, Germany. The assembled ESC-A upper stage now consists of 3 cylindrical segments, 5.40 meters in diameter, and an empty weight of 4.6 tons. Inside are the HM-7B engine, hydrogen and oxygen tanks, and the brain of the rocket, the VEB. The upper stage is now prepared for transportation by road to the port in Bremen. The huge dimensions, the sensitive technology, and the explosives for stage separation regularly make transporting the upper stage by road a significant challenge. For the journey, the stage is secured in a special transportable container. This is then sealed so that it is pressure and dust tight. Under no circumstances may moisture or dust particles penetrate the container during transport. The slightest damage to the rocket components could have catastrophic consequences. Flashback, June 4th, 1996. The first Ariane 5 stands ready for its maiden flight. On board, 4 research satellites. Everything is going to plan. The Vulcain engine ignites correctly. The boosters fire up after 7 seconds, and the Ariane 5 lifts off. It follows its programmed flight path, traveling precisely as intended. But then, there's an unpleasant surprise. "37 seconds into the flight, a fault occurs in the Ariane 5's electronic position control system. The self-destruct sequence is triggered, and the rocket explodes. The inquiry into the accident found that there had been a careless error in adapting the software from the Ariane 4. The acceleration of the Ariane 5 was much stronger than that of its predecessor. A too high measurement value first caused the software to crash, and then the rocket itself. After a few minor glitches and the loss of a main stage outside the Earth's atmosphere in 2002, the Ariane 5 overcame its teething problems, and all subsequent launches have been successful. The Airbus site in Bremen, midnight. A number of police cars arrive. The convoy carrying the upper stage starts to make its way to the port. Before the heavy load can leave the site, the route needs to be precisely coordinated. Then they can roll. Though these transport operations are routine for those involved, each one of the annual 6 to 8 journeys has its own challenges. The convoy always travels the 17 kilometers at night, as the route requires motorways, roads, and railway lines to be temporarily closed. After only a few minutes, they arrive at the first obstacle. A junction with an overhead tram power line has to be crossed. The power is switched off, and with the help of 2 hydraulic platform vehicles, the cable is raised to 6 meters. Before the convoy can pass through, the height is checked again. The special container is now lowered by 10 centimeters to create a little more space beneath the power line. The hydraulic chassis can vary its height by up to half a meter. After 3 minutes, this first obstacle has been overcome. The unwieldy combination, 20 meters long and 6 meters wide, crosses the junction diagonally to avoid the traffic lights. The journey through Bremen suburbs continues. The special container now has to be realigned, a tricky task for driver and attendant. Each axle has to be adjusted individually. A few low-hanging branches now get in the way, but they are hardly going to pose any problems to this colossus. After 45 minutes, the convoy grinds to a halt. A low bridge is blocking the route. So up it goes onto the motorway, specially closed for the occasion. The transporter takes the slip road up the wrong side of the motorway. Even this comfortable road width is only just wide enough for the enormous container. Time for a short break for the escort team. The few kilometers along the closed motorway gives the convoy the opportunity to travel at its highest permissible speed of 21 kilometers per hour. Back on the normal road, and it's down to walking pace again. The transporter drives over or around minor obstacles like roundabouts with extreme care, as vibrations need to be avoided. As the route is used 6 to 8 times a year, the road signs are all designed to be put up and taken down quickly. Ahead of the port, there is now only one level crossing. But this one has an automatic system for raising the power lines. After 1 hour and 50 minutes, the convoy finally reaches the terminal. In the final 500 meters, it passes mountains of containers. Past the storage warehouses, it finally arrives at the pier, specially constructed for the Ariane program. The driver and his team will spend the remaining hours until daybreak at the port, waiting. The next morning, the special French roll-on, roll-off ship is ready and waiting for loading. The MN Colibri is 116 meters long and 20 meters wide, and has been deployed on the Ariane program since the year 2000. Bremen is the first port of call for the MN Colibri on her way to French Guiana on the other side of the Atlantic. The container with the upper stage is now driven up a ramp onto the ship. The hold is still more or less empty, but in the next few days, it will soon fill up with the individual components of an Ariane 5 launcher picked up from various ports in Europe. The Colibri was built specially for transporting the rocket components.
Lassen wir so stehen, ist gut.
The entire container is set down on the floor completely and secured by the crew to prevent it slipping in rough seas. Following the handover of the container, the transport specialist's long working day is over, and the Colibri is ready to sail. So now it's full steam ahead for the Colibri. Together with her sister ship, the MN Toucan, she commutes back and forth in a 14-day rhythm between South America and Europe. The route to French Guiana takes the Colibri down the Weser into the North Sea to the port of Rotterdam in the Netherlands. From here, she heads to Le Havre in France, where the main stage of the Ariane is taken on board. In the Italian port of Livorno, she picks up booster and fairing components. The crossing to Kourou then takes another 5 days. Coming up in part 2, the individual components arrive in Kourou in French Guiana. At the spaceport, all the elements are put together. The satellites the rocket will be carrying are flown in by plane. Transport to the launch pad takes place under the most stringent safety precautions. And after final fueling, countdown is initiated for the launch of yet another Ariane 5 into space.
3, 2, 1, allumage Vulcain.